Owon have had a bunch of power supply models in their lineup for a while, but this new edition, the SPE series, caught my eye because it's in the affordable budget range, and I really wanted to give this one a try to see if it's any good and if it will earn its spot on my workbench. So join me in this video to learn more about it. Inside the box you get the power supply itself, a mains IAC cable and a USB cable, together with the user manual and a spare fuse. There are no test leads included, which is good because typically those included test leads are pretty low quality and you wouldn't want to use them anyway. The enclosure is made of metal with the exception of the front panel, which is this glossy plastic. Generally, it gives me a good feeling. There is nice metal work happening here. There are nice rubber feet to prevent it from sliding around, and I'm definitely liking how this is built at first sight. I quite like the general layout of this power supply unit. The LCD is located at the top of the front panel. We get some soft keys, which are nice and rubbery. There seems to be enough spacing between the keys. The on-off switch that controls the output has an LED behind it, but they somehow decided it will be a good idea to have it shine blue when the output is on, and I would very much prefer if manufacturers would stick to red-green LEDs for the on-off buttons on power supplies. The rotary knob is pushable, and we'll see if that's used in any way in the GUI, but the feeling is that of cheap plastic. I would have preferred a nice rubber or metal knob on here, but hey, let's not forget the price range of this unit. There is a USB 5V 1A port on the front panel, which I expect to be power only, but that's a nice touch because you often need to power some USB devices on the workbench. Would have been nicer if it would be rated for 2.4 amps, or if the power supply included like a current and voltage measurement on the screen for the USB port. But still, it's nice to have this 1A port on the front panel. The banana plugs they use do unscrew, and they do have a hole so you can insert a wire for easier testing. They feel just okay, not great but not terrible either. There is an earth connection banana plug, but because they decided to place that in the middle of this arrangement between the positive and negative output, it means you can't use one of these plugs with a standard 19mm spacing. It looks like they used more like 21mm spacing, so that's a bummer. The sponsor of this video, Altium, is one of the most advanced PCB design softwares on the market. It has some pretty advanced features which enable collaboration among multiple team members, so there is no wonder they are a popular choice in the professional PCB design world. If you're interested in trying out Altium, check out the link I've placed in the description below to sign up for a free trial of Altium. On the back of the unit we have the mains IEC input with a fuse socket and an on-off switch, the USB connection for a computer, and we also have the cooling fan, which seems to be pushing air inside the case with the exhaust through the side vents. I know having the on-off switch on the back is not ideal, but seems to be the standard for these compact units. The other Owon power supplies, which are more expensive, they all have the on-off switch on the front of the unit, and I would very much prefer a slightly wider body to accommodate the on-off switch on the front, but that's just me. If you agree, let me know in the comments below, and while you're there, why not smash that like button, because it only takes you a second to do and it's free. There are 4 options you can get in this lineup, but as far as I can tell, they are not universal input voltage, so you need to get either the 110 or the 230 volts AC version, because if you pick the 110 version, you get an input range of 93 to 127 volts AC, and if you pick the 230 volts AC like I have here, you get a range between 187 and 253 volts AC. And I wonder why they went with these 2 separate options instead of designing like a universal input switch mode power supply. Could be cost, could be efficiency, because there's definitely an efficiency difference between the two. I don't know, let me know in the comments what you think about this, but generally it's not a big issue for the end user, because it's not like I'm going to travel to a 110 volt country with all of my test gear. You get two main output voltage ranges, 0 to 30 volts and 0 to 60 volts, with up to 5 amps or up to 10 amps depending on the model you select. But there is a catch. That doesn't mean all models can output the full power at voltage times current at the same time. That's where the different models come into play. You have a 150 watt, a 200 watt and a 300 watt model. And I have the SPE6102 here, and this one is 200 watts rated. So even though it can do 60 volts up to 10 amps, it's limited to 200 watts, so it can do 60 volts but only up to 3.3 amps, or it can do 10 amps but only up to 20 volts. Whichever values you choose will be limited to that 200 watts envelope. In terms of specs, these are pretty casual specs, nothing special here. Less than 30 millivolts peak-to-peak noise level, a set resolution of 10 millivolts and 1 milliamp, with the same for reading. Accuracy is 0.1% plus or minus 20 millivolts or plus or minus 10 milliamps, but to be honest, for general hobby use, these specs are good enough. I mean, they certainly are good enough for all of my project, but there is an asterisk which is not mentioned in the included spec sheet that comes with the power supply, but it is included on their website, and there's this very small asterisk after the specs on their website where they tell you in small text that the output noise is measured with a couple of capacitors added to the output terminals, and I don't think that's normal. A spec should be quoted for whatever the instrument can do on its own, but we'll see how that works later on when we put it through some testing. Turning on the power supply reveals a weird flickering on the on-off button LED. I don't know what's up with that. I hope the camera is picking that up, but other than that, it's a rather decent GUI implementation at first sight. The display is 2.8 inches wide and has a resolution of 240 by 320, which is nothing to write home about, but honestly decent for a power supply of this size. Viewing angles are very good for vertical angles, but not so good for horizontal angles, where it starts to become pretty bad. So it all depends on where you position this on your workbench to be able to get a good view. Screen refresh or update rate seems to be about 2 or 3 frames per second, which is not great. I would love to see more, but probably expected in this price range and probably limited by the microcontroller they used. I also noticed the cooling fan is quite noisy. You'll notice it right from the start. It's not the worst I've seen, but certainly noticeable and annoying in my opinion. They do have a so-called intelligent speed fan control, so why couldn't they just have the fan run at lower speed for low power operations, or have it completely off when the PSU is idle? I'm sure they can fix that with a software update if they want to, and I hope they will. It seems like the default screen mode is to show this graph of voltage and current over time, and we have the actual current values, the current and voltage values shown here, and the set values and the limit values on the bottom row. And that seems like a reasonable layout. And on the top bar we have the on-off indicator, but that's better visualized through the switch indicator. We get the current mode, CC or CV, the time while the output is on, and a power indicator. Strangely, for example, with the output set at 10 volts, I get a 0.1 watts figure with the output floating, so there is something on the output of this power supply inside the unit that's drawing a little bit of power, and that gets measured. By hitting the display button, you can switch to the second display view, which brings the actual current and voltage values in the center of the display, gets rid of the graph, and I think I'll be using the PSU mostly in this mode, but what's annoying is that it resets to the previous mode when you cycle power. I just wish it would remember the display mode, because I wouldn't be using the graph display mode unless I want to track some variations over time, which is not very often. There's also this memory function which can store up to 5 user adjustable presets that can be recalled and applied by long pressing the rotary knob, and that can be useful for tasks that are repetitive, But at my workbench, however, tend to just manually adjust every time I need to change settings. I just don't do a lot of repetitive testing or tasks. They also include a waveform function which can be accessed by long pressing the memory key, and you can have these individual pre-programmed steps which are cycled at preset periods of time. Might be useful for some testing purposes, but from what I can tell, there is quite a lot of capacitance on the output of the PSU, so don't expect this to be capable of sharp falling edges. By default, the output gets disabled when you power cycle the unit, but you can set it to automatically enable on power on by long pressing the on-off switch. That's something that's best left disabled, in my opinion, if you don't necessarily need it, because you can fry some circuits by leaving that on if you forget about it. Also, if any of the protection thresholds are tripped, the output will turn off automatically and it needs to be manually re-enabled. I feel like I've talked quite a bit about the general presentation of this power supply and its features, but surely you must be curious by how it looks inside, what the build quality is like, so here we go with the teardown. Quite a clean looking construction at first sight, but let me take a closer look at this board and readjust the camera angle. This certainly looks good inside, and let me start with the good stuff. A few nice details that I noticed. The metal work looks good and precise. Look at how they left the paint off in these contact areas between the different parts of the enclosure for good earth connection. There is nice earthing going on this internal metal post with a screw, and check out this nice detail here in how the front panel connects with the rest of the enclosure. This diagonal cutout slot just seems like a very nice idea and brings the whole enclosure together. Connectors seem to have Celastic on them to prevent them from coming off. The wiring is generally pretty clean looking, with the exception of the missing insulation over the mains connections. I like how the main PSU board is positioned vertically with the fins oriented such as to get good airflow from the cooling fan. And it looks like we have a total of 3 PCBs in this assembly, so let me disconnect a few of these wires so we can take a closer look at these boards. Looking at the front panel PCB, soldering generally looks clean. There is very little flux residue left behind. It seems like they might be using the same front panel across the different models, just with different firmware, as mine is labeled SPE3051, which is their base model, and it has a date code of April 2021. They're using a Giga Devices branded ARM micro in here. It's the F303 model, and that totally makes sense. I bet you can still order these, but good luck trying to buy an ST micro. We have a factory bodge in here. Given how the date code on this is from April 2021, this is probably something they would have fixed by now in the current production version. We have a bunch of op amps in here. These 3 top ones are SGM OP17C. These are high voltage, low noise rail to rail, and these 2 are 33078s, low noise dual op amps, and it looks like we have a local DC to DC converter in this area. Maybe it's putting out the 5 volts needed for the USB port, I don't know. There's also a 7805 in here, and I'm hoping it's not used for the USB port because it would get very hot. Let me check with a continuity tester.
A few moments later.
I'm getting a continuity from the DC to DC inductor output to the plus 5 volts. So as expected, the DC to DC is driving the 1 amp 5 volt USB port on the front panel. They're using 16 AWG wire for the main output connections, and I guess this is sufficient for the 10 amp output of the power supply. I don't think there will be much on the other side of this PCB. Probably no components at all, so I don't think it's worth taking this part further. Let's move to the small USB board for the PC connection. This ties in via this flat flex directly to the front panel PCB, and this is likely a UART interface that's coming into this little board, which goes through this dual channel digital isolator and then connects to a CH340 USB to serial bridge. So yeah, this USB board is isolated. The two ground planes are, however, connected via this capacitor. The main PSU board is pretty interesting, and let me start with the input protection features. It's got all that's needed here. It starts with this nice big varistor and NTC combo. Then we have an X-class filtering capacitor, a nice looking common mode choke with some beefy copper visible here, and this has a pair of Y-class capacitors across each side. Then it goes through a bridge rectifier, and it is eventually filtered by these big filtering capacitors. The brand of these caps, and for all of the caps used in this unit, is CHMEC. Can we call that a no-name? I don't know. Let me know in the comments. They're probably a no-name for me, but they are 105 degrees C rated caps, and they do have discharge resistors, which is a nice touch. Once again, on this board, it's mentioned SPE3051 power board version 1.3, and this one has a date code of September 2021. So once again, this makes me think that they're probably using the same power board for all of the version in their lineup, but this one has a more recent date code, and this one here, 42nd week of 2021, makes it a fairly recent production date. After we get our DC voltage from the filtering caps, I believe we are dealing with two separate switch mode power supplies here. And let me start with the smaller auxiliary one, which is in this area. It must be producing something like 12 volts. I haven't measured it, but that would be my guess, and that rail must be used to power the circuitry inside the power supply unit through further stepping down via local regulators. And this small power supply is powered by a Power Integrations, I believe, a TNY288, and it's situated in this area of the PCB. Our main switcher, however, relies on these two MOSFETs, which sit on the input, and the bigger transformer, as well as a diode rectifier on the output, and this third MOSFET, which sits next to the secondary side rectifier. I believe this is used to switch the output on or off. And we also have an inductor and capacitors to filter the output, and here is our shunt resistor for measuring current. What's unusual is that I couldn't find any power supply controller chip, no PWM controller, nothing like that. I mean, that's what you would expect in such a product, right? That's what we have in the Gopher power supplies. But here we just have op amps, we have comparators, and another Giga Devices microcontroller, this little guy here. And this time it's a GD32E230, which doesn't seem to have any specifically useful features other than maybe being very affordable and available, but I believe they rolled a somewhat discrete implementation switch mode power supply design based on these op amps, where they get voltage and current information, this comparator where they likely set the desired reference, and this micro taking care of controlling the power supply unit and varying its output. Maybe also taking care of some other housekeeping tasks on this board, like the cooling fan, maintaining comms with the front panel for reporting values and receiving commands. It's reading temperature measurements from this thermistor placed on the heatsink, and the input side MOSFETs seem to be driven through this smaller transformer, but their path goes through some logic gates, and it eventually ends up in the microcontroller area. And it makes me wonder why they went with this option instead of using an off-the-shelf switch mode power supply controller chip. I mean, yes, they can probably get this micro for cheap, but is that enough to cover the development costs for the firmware instead of rolling a known working solution? Or maybe there are other advantages that make it work, like the fact that they can have multiple models with different output capabilities with maybe just different firmware. I would love to hear your thoughts about this in the comments below. I mean, they didn't even bother getting a micro that would at least have some built-in op-amps and comparators or better ADC capabilities, which would have saved them on the cost side of things. If I'm right and they're just using different firmware for the different models that they sell, this means these power supplies are potentially hackable, where you can order the smallest rated version and through a firmware upgrade hack it into a more potent version. It could also be that it's exactly the same firmware inside, just with some resistors that let the board know which version it is and which set of rules to load in the firmware. And I believe I have not mentioned, this is the cooling fan driving circuit. It's obviously PWM controlled. They even have an optocoupler in here. But even after running idle, these heatsinks do feel warm to the touch, so I believe that's why they do not turn off the fan completely. The board is generating some heat even when running idle, so maybe my best option is to just replace this fan with a more silent version. So I have the unit back together, and in terms of testing, I will just show you the results of the tests I run, and I'll quickly show and mention the test methods. First, voltage accuracy test measured against my reliable HP34401A. I noticed something strange with the Owon here. I've measured a bunch of different points with no load, and it just seems like the set accuracy, the value that you actually set down here when compared to the values measured at the output with my HP, is very accurate, with the worst results being just 10 millivolts out. Now remember, the claimed spec is better than 0.1% plus or minus 30 millivolts, and what's strange is that the measured accuracy, so what's shown in the middle of the screen, is much worse. I mean, it's only outside of spec for the very low ranges with 40 millivolts, but I find it strange to see different values between set and measured voltage with no load. It just makes me think that they might be using two measurements or measuring in 2 points, one for the set and control loop and another one for the measured displayed value. And the two do not correlate, but I would love to hear your thoughts in the comments about this issue. Next up, I measured current accuracy, shorted the output through my 34401A for up to 2 amps, and then switched to my Fluke 87.5 for up to 10 amps. Results once again show very good accuracy for the set accuracy, so the value you set compared against the value measured externally, with the worst error being just 4 milliamps out, way below the claimed 10 milliamps. However, once again, we have that measured accuracy error, a difference between what's measured by the PSU shown on the display and what is actually at the output. That is even more visible if we calculate error as a percentage of reading. Now, a good chunk of this error correlates to that constant current offset shown on the Owon screen. It may be that it just needs calibration, and it once again might support the theory that they're using two separate measurement points, one for the set and control loop and another one for the display. But I can't find any good reason why they would do that. And if you wanted to somehow correct for this, there doesn't seem to be any user accessible calibration function, at least not mentioned in the user manual. Next up, I tested for voltage or current overshoot in various scenarios. Here is the test for voltage overshoot with no load. This is soft key turn on, and there is no voltage overshoot here. And hard power switch turn on, again, no voltage overshoot. They do have this 5-second delay from the moment you start the power supply until it automatically enables the output. So they are waiting for the PSU to be up and stable before enabling the output. But as a side note, this waveform is not clean. Look at the amount of noise we have in there. I've also tested with an 8 ohm load, about 0.6 amps. No overshoot either, just a lot more noise on the output. Now, testing for current overshoot, I'm using a mixing current probe. PSU is in constant current mode, set to limit at 250 milliamps. Both soft key turn on and hard power on switch shows no current overshoot. However, plenty of noise on this waveform. And here is how the output looks when we have a sudden change in load. So first with the removal of the load and then adding a resistive load in the circuit. We get no voltage overshoot in both cases, just a lot of switching noise. And now for the output noise measurement, here is my test setup. Oscilloscope probe connected as close as possible to the output terminals. 20 MHz bandwidth limit on. With no load we get roughly 100 millivolts peak to peak of ripple. I mean, there are higher peaks, but that's where I see the majority of the signal concentrated in the 100 millivolt range. And if I zoom in, we can also see these peaks. I also measured with a 1 amp load into a resistor, constant current mode, and the waveform I got is horrible. 500 millivolts of peak-to-peak noise, and testing again in constant voltage mode showed a similar waveform, so I'm not too happy with what I'm seeing here. I also ran a small stress test on this, running the power supply at its full 200 watts rated output for half an hour using my electronic load, and it survived just fine. I mean, the fan was blasting at full speed, it was very noisy. The case got just a little bit warm to the touch, but no issues whatsoever. You also have the capability of connecting this power supply to a PC for control and monitoring through this isolated USB port, but myself, I'm not a big fan of that, especially if we're talking about a power supply. Considering the types of projects that I build, I very rarely need to do that, but if you're into testing or automated testing, then you might be interested in that. But then again, if you're into automated testing, you're probably going to use a higher quality power supply. So for that reason, and the fact that this guy uses the NOI Visa software package, which I dislike, I'm not going to cover the software, the computer connection and the software in this video. So now to give you my final thoughts on this power supply, let me start with its cost. I paid roughly $135 shipping and VAT included for this power supply. The build quality is definitely good. I like the form factor of this. The functionality is good. Generally, I like the graphical user interface. It's got pretty good accuracy for set voltage and current. Not so good for the measurement part. It doesn't have any dangerous overshoots in terms of voltage and current. Plenty of protection features on the input of the power supply. But where this unit disappoints is in its output noise levels. It's crazy how much noise we're seeing on the output of this power supply, and take it as a joke or not, we're also seeing a lot of noise from the cooling fan. Yes, you might argue that I have not followed the small asterisk. They mention that the output noise is coated with some external capacitors added to the output terminals. But is that really okay? Should we accept that kind of stuff from manufacturers? I don't think so, because when I'm using this power supply to power something, I'm not strapping capacitors to its output terminals, so I don't think that's a fair way of coating your specs. You can still get a Go for NPS1601 power supply with excellent low noise output for roughly half the cost of the Owon. Yes, it doesn't have the same functionality and it's not as polished, but if you need a low noise power supply, go for a Go for. Now, if you don't really care about the output noise, you could go for the Owon. You could also try to improve the output filtering to lower the noise, but I wouldn't use this power supply to power anything other than devices like motors or stuff that isn't generally affected by that amount of noise. If you still decide to get one, I will provide the link in the description of the video. And with that, it's time to end this video. Thank you for watching, and don't forget, you can support the channel with as little as $1 per month on Patreon.